October 1994. Civil engineer Kenneth Wright has just arrived in Cusco on a 7 a.m. flight and is meeting a Peruvian archaeologist named Alfredo Valencia Zagara over coffee before the day is out. They have a permit. They have a research plan. And within days, they will be at Machu Picchu with excavation equipment, digging straight down through the main plaza to find out what the Incas built where nobody could see it. Wright has spent his career designing water management systems. He knows what sophisticated hydraulic infrastructure looks like. He suspects, based on what the visible construction tells him about the engineering judgment of the people who built it, that there is something extraordinary below the surface. He is not wrong. But what he finds when the excavation passes through 3 feet of carefully placed topsoil, then through 2 feet of sandy gravel, then into a dense matrix of white stone chips, what he finds changes the way he understands every square meter of the site above him. This rock turned out to be white because it was white granite originally, before turning color with age. So while we look at Machu Picchu today and see gray buildings, when it was built, it was white granite. The white granite chips in the drainage matrix were recycled construction waste. The chips and fragments produced during the shaping and fitting of the granite blocks used to build the walls above. The Incas had not disposed of this waste. They had used it as the critical component of an underground drainage system. A porous, permeable matrix at the base of the engineered fill layer that would accept the water, percolating down through the topsoil and the gravel above it, and route it away from the foundations of the walls. The waste from the most visible part of the construction was the raw material for the most invisible part of the construction. And the invisible part was the reason the visible part was still standing. Without good drainage, there would be no Machu Picchu existing today, Wright concluded. It is not an overstatement. Machu Picchu sits in one of the wettest mountain environments in the Andes, receiving up to 2,000 millimeters of rainfall annually. The site is on a steep ridge subject to frequent seismic activity. The combination of saturation and seismic loading that would face an inadequately drained foundation in this environment would, over 5 centuries, guarantee the complete failure of any conventional stone construction. The site exists today because the Incas understood, through whatever combination of engineering knowledge and accumulated experience, that the problem of building on this mountain for eternity was primarily a drainage problem, and that solving the drainage problem required building a hidden engineered world beneath the visible one. Understanding the full scope of what has been found beneath and around Machu Picchu requires following both the engineering evidence and the more recent discoveries that modern instruments have revealed in the jungle surrounding the main citadel. These are complementary stories, one about what was built deliberately below the surface and one about what was hidden by centuries of jungle growth above the surface, and together they describe a site whose actual extent and sophistication were significantly underestimated by every account produced in the century following Hiram Bingham's 1911 visit. Begin with the geological foundation, because the geology is the precondition for everything else, and because it is now understood with a precision that fundamentally changes how the Inca engineers' choices can be evaluated. The geology of Machu Picchu area is characterized by granitoid bodies that had been emplaced in the axial zones of the main rift system. Deformation of the granite, caused by cooling and tectonic phases, originated 4 main joint sets, regularly spaced at few decimeters to meters. This specific geological context, granite deformed by cooling and tectonic history into 4 sets of regularly spaced fractures, is what gave Machu Picchu its building material. The joint sets created a 3-dimensional network of natural fracture planes that divided the granite into roughly rectangular blocks. Inca builders did not need sophisticated quarrying technology to produce rectangular building stones at Machu Picchu in the way they needed it at Aswan for Egyptian granite work, or at Sacsayhuaman for the massive polygonal blocks. The joint pattern of the Machu Picchu granite produced rectangular blocks as a natural consequence of frost action, root wedging, and the slow mechanical work of weathering along fracture planes. The Inca builders recognized this geological gift and selected the ridge specifically because the granite provided the raw material they needed in the geometry they required. 2 principal faults are named for the 2 prominent local peaks, Huayna Picchu Fault and Machu Picchu Fault. These high-angle reverse faults formed a wedge-shaped structural block relative to their namesakes. This block, or graben, is the structure on which the ancient Inca people built their city. The Machu Picchu Fault influenced the location at which the Machu Picchu spring emerges. The fault system did more than provide building blocks. It created the hydrological infrastructure that made permanent occupation of the ridge possible. The Machu Picchu Fault caused fracturing and crushing of the adjacent hard granite rock, which in turn resulted in a natural spring water source on the north slope of Machu Picchu Mountain. The spring, which emerges at elevation 2,458 meters, slightly above the main citadel, is the product of the fault's disruption of the granite's impermeability. Rainwater that falls on the ridge and surrounding slopes infiltrates through the fractured zone of the fault, accumulates in the higher porosity rock, and emerges at the surface where the hydraulic gradient and the geology direct it. Without the fault, no spring. Without the spring, no water supply. Without the water supply at higher elevation than the citadel, no gravity-fed water system. Without the gravity-fed water system, the entire hydraulic infrastructure that gives the site its ceremonial fountains, its agricultural irrigation, and its drinking water cannot exist. The ancient citadel is built near the intersection of two geological faults, which facilitates the retention of rainwater. The choice of this water source was not accidental, as the ancient engineers had to select a spring located at a higher elevation than the citadel. The Incas understood that a spring feeding a hydraulic system must sit above the system it feeds, that gravity is the force that moves water through canals and fountains without pumps. Finding a spring at the right elevation in the right location, connected to the right ridge for construction, was not a matter of finding any mountain with granite. It was finding the specific geological configuration that satisfied all constraints simultaneously. The fault system at Machu Picchu satisfied them all. The Machu Picchu geologic fault set the stage for the Inca water supply source by helping create the ancient primary spring water supply at elevation 2,458 meters and east of the ancient perimeter wall. From the spring, a 749-meter aqueduct, a carefully sloped stone-lined canal, carries water into the citadel and distributes it to 16 ceremonial fountains arranged in a descending sequence from the highest point of the urban sector to the agricultural terraces below. The fountains are not purely ceremonial in function, though their ceremonial dimension is primary. They are working hydraulic features, calibrated for specific flow rates, equipped with hydraulic engineering details that reflect a sophisticated understanding of open channel flow. To assure that the two ceremonial fountains would not overflow during periods of excessive water yield, a hydraulic bifurcation was built upstream of the upper fountain so that excess water would be diverted into a stone-formed conduit for discharge to an adjacent drainage channel. This is evidence that the Inca engineers understood the fundamental mechanics of water flow and that they had the ability to enhance the hydraulic operation of the fountains to account for periods of low flow. A hydraulic bifurcation, a specific engineered junction in a water distribution system that divides the flow between two downstream paths with the division ratio determined by the relative size and slope of the two paths, is a piece of hydraulic infrastructure that requires understanding how flow distributes through branching channels and how the geometry of the branch points determines the proportion each branch receives. The Inca engineers did not have the Bernoulli equation or Manning's formula. They had empirical knowledge, tested against the behavior of water in the specific channels and gradients they worked with, accumulated over the construction of hydraulic infrastructure across the entire Inca Empire. That empirical knowledge was sufficient to design a bifurcation that has functioned correctly under the full range of the site's hydrological variability for 5.5 centuries. Wright's 1994 excavation revealed the underground component of the same hydraulic sophistication applied to the challenge of managing not the water supply but the storm water, the rainfall that falls directly on the site and must be moved through and away from the construction without destabilizing the foundations, saturating the fill, or producing runoff that would erode the terraces. 130 or more strategic drainage outlets built into the original wall construction thread through the fabric of the visible masonry, specifically designed to accept water from the underground matrix and route it through the walls to the exterior drainage channels. The outlets are built-in features of the original construction, not retrofitted, not adaptations to observed failure, but planned as integral components of the wall design before the first block was laid. The technical challenge this represents is significant. Every wall at Machu Picchu that required drainage outlets, which is most of the walls that retain earth or receive groundwater from upslope, needed to have those outlets correctly positioned relative to the underground drainage matrix and the exterior drainage channels before the wall was built. Positioning drainage outlets correctly requires knowing, before construction, where the underground water will accumulate, at what elevation it will reach the wall base, and what path the outlet needs to follow through the wall to connect the interior matrix to the exterior channel. This is design-ahead engineering, the kind that requires understanding the hydraulic behavior of the completed system well enough to specify its components during construction, when the completed system does not yet exist. The geophysical investigations confirm the geological and geomorphological assumptions on the original shape of the area. Results from ERT and ground-penetrating radar located the bedrock at a depth from 0 to 3, 5 meters below the current ground level. The 2023 scientific report study by Massini and colleagues, applying electrical resistivity tomography, ground-penetrating radar, magnetic surveys, satellite multispectral imaging, and UAV imaging simultaneously to the main citadel area, built the first complete three-dimensional model of the subsurface environment that the Inca engineers worked with. The model shows the original topography of the ridge before construction began, more irregular, more steeply varied, less organized than the finished site. The Incas imposed their engineered topography on top of this natural one, grading and filling to create the level plazas and uniformly sloped terraces. while simultaneously installing the drainage infrastructure that would keep the fill stable and the construction viable. The scale of the earthworks implied by the difference between the natural topography and the finished topography is substantial. Moving the quantities of material implied by a 2 to 3 meter depth of engineered fill across the entire main citadel, selecting it for drainage properties, placing it in the correct stratigraphic sequence, installing granite drainage chips throughout, threading drainage outlets through the wall fabric, required a construction operation whose scale and coordination were comparable to the wall construction above. This is why 50 to 60% of the total construction effort lies underground. The visible walls, impressive as they are the smaller engineering challenge. The invisible infrastructure is the larger one. Now move outside the main citadel to the jungle-covered slopes and valleys where drone-mounted LiDAR has been revealing the full extent of what the Machu Picchu complex actually was. The Chabamba ceremonial complex was known before the LiDAR work. It is a site of ritual fountains and bathing platforms in the Urubamba Valley, approximately 5 miles from the main citadel, associated with the ceremonial processing of pilgrims approaching Machu Picchu along the Inca Trail. What was not known was the extent of associated infrastructure surrounding the known features. The LiDAR scans revealed about 12 structures, all within about 60 feet of the main ceremonial part of Chabamba. "They were so close, and we didn't even know they were there," said Sichkowska. 60 feet from known structures that have been the subject of archaeological attention for decades. The limitation was not the coverage of archaeological attention. It was the capability of ground-level survey in cloud forest terrain where visibility is measured in meters and where archaeological features disappear completely under vegetation within years of abandonment. Earlier, airborne LiDAR attempts at Machu Picchu in 2016 by the Peru LiDAR project produced disappointing results due to dense understory vegetation. The 2024-2025 discoveries succeeded because of improved sensor technology, modern multi-return LiDAR systems with higher penetration capability, optimized flight parameters at lower altitude, slower speeds, and increased overlap, and advanced processing algorithms with better vegetation filtering and ground detection. The multi-return LiDAR systems that made the difference are systems that record not just the first return of the laser pulse, the top of the vegetation canopy, but multiple returns from the same pulse as it penetrates progressively deeper into the canopy before eventually reaching the ground. In forest terrain with complex vertical layering, emergent canopy, mid-canopy, understory, and ground layer, single return systems capture mostly the canopy and miss the ground entirely. Multi-return systems capture enough ground returns, when processed with advanced filtering algorithms, to reconstruct the topography of the ground surface beneath the canopy with sufficient resolution to identify archaeological features. The laser scans also revealed stone channels running partly underground that supplied water throughout the Chabamba site. LiDAR scans have revealed an intricate network of stone channels running partly underground that supplied water throughout the Chabamba site. Using advanced hydrodynamic modeling, researchers virtually poured water through these ancient channels to understand their function. Precise flow control. Small channel dimensions prevented overflow while maintaining symbolic water flow. The hydrodynamic modeling of the Chabamba channels is a methodological innovation that extends the interpretive capability of LiDAR survey beyond simple structure identification. LiDAR provides the three-dimensional geometry of the channels, their slope, their width, their depth, their routing through the landscape. Hydrodynamic modeling uses that geometry as input to simulate water flow, applying the physical equations governing open-channel hydraulics to determine how water would have moved through the channel network under various flow conditions. The result is not just a map of where the channels are, but a quantitative description of how they functioned, what flow rates they sustained, how the flow was distributed between branches, whether specific features represent overflow control or flow bifurcation, analogous to the hydraulic bifurcation at the main citadel. The engineering sophistication of the water management at Chabamba, a satellite site, not the main citadel, reflects the same systematic application of hydraulic engineering principles visible at the main citadel. The 12 previously unknown structures surrounding the main ceremonial complex were not informal additions. They were components of a planned infrastructure that included water supply, distribution, ritual use, and presumably accommodation, and support functions for whoever staffed and used the site. Among the most significant discoveries is a 2-kilometer road that displays layout characteristics typical of Inca construction techniques. Researchers have also investigated a distinctive zigzagging pattern along its route, which suggests the road may have been built during the Inca Empire. The zigzag pattern is a specific Inca road building technique employed on steep terrain. Rather than ascending straight up a slope which would require unsustainably high gradients for loaded transport, zigzag roads traverse the slope at a shallower angle, reversing direction at each switchback to gain elevation while maintaining a gradient manageable by human carriers and pack llamas. The presence of the zigzag pattern is one of the primary diagnostic features that identifies a road as Inca construction rather than modern or colonial origin. The road network now identified in the Mandor Wall area extends the documented Inca road infrastructure in the immediate Machu Picchu region beyond what was previously mapped. And it implies connections between the main citadel and facilities in the Mandor Valley that have not yet been fully characterized. The Inca road network was not built for casual movement. It was infrastructure of the imperial administration, moving goods, people, and information on a schedule determined by imperial authority. Roads led to and from places that mattered. The 1-2 kilometer road in the Mandor area, built to Inca construction standards, was connecting something to something else, and the full identification of what those somethings were is still in progress. LiDAR analysis has revealed that Machu Picchu was not an isolated mountaintop retreat, but the hub of a geographically vast complex extending far beyond the visible stone structures tourists see today. The engineering picture that emerges from this combination, the underground drainage system, the geological exploitation of the fault system, the hydraulic infrastructure above and below ground, the satellite ceremonial complex at Chalchabamba, the road network in the Mandor area, and the remaining uncharacterized structures that the LiDAR is revealing, is of a planned, integrated, systematically engineered royal estate whose functional scope was far larger than the main citadel footprint. Ken Wright's 1994 finding of white granite chips at the bottom of the drainage fill was not just a discovery about drainage engineering. It was the first clear evidence that the Incas designed Machu Picchu's invisible systems with the same systematic intelligence they applied to its visible ones, that they recycled the waste from wall construction to create the drainage matrix that would protect those walls, that they considered the hydrological behavior of the entire engineered fill above the bedrock as integral to the success of the construction above it, and that they understood all of this before they began. The golden bracelet at the very bottom of the excavation was placed there before the drainage matrix was built, before the fill was placed, before the topsoil was laid, before the grass grew, before the first wall was raised. It was placed as a ritual acknowledgement that the invisible engineering was primary, that what was being built in the earth was the foundation that made everything else possible. 5.5 centuries later, the engineering has not failed. The drainage matrix is still moving water. The 130-plus drainage outlets in the walls are still functioning. The spring is still flowing through the 749-meter aqueduct to the 16 fountains. And the LiDAR drones are still revealing, season by season, more of what the Incas built in the places where the visible ruins give no indication of what is concealed beneath the vegetation. Subscribe, because what has been found below Machu Picchu changes everything about what we thought we understood about what Machu Picchu is.